Swayam Prabha. Digital India. Educated India.
Okay, good morning everyone. I hope you had a nice rest yesterday and ready for another round. Okay, so I'm gonna retake it where I left it, so just maybe going back to the original schedule. I'll do the same as yesterday, so interrupt me at any time. After, 45 minutes or so, I'll do a 5-minute break, and then we'll continue, and then the coffee break. So today is more about implementation and practicalities, but I'm gonna finish a few things that I didn't have time to discuss yesterday, and then we'll move on to the applications, and then the seminar in the afternoon. So I left it here. We were talking about adaptive remeshing, and then the next thing is the irreversibility condition. So of course, phase field is kind of a damage model, so the phase field variable is like a damage variable, so it goes from 0 to 1. And I mean, it can happen in some materials, but it's very rare. Normally, damage is an irreversible process. If you damage something, it doesn't reheal. Some things can reheal, but it's rare. So often in damage models, you need to make sure that your damage variable, in this case the phase field, just goes up, never goes down. There's no reason why this would not happen in the phase field equation, right? So if, for example, you lower your strength and density, your driving force for fracture, then it could be that your phase field doesn't fulfill this irreversibility condition. So there's multiple approaches in which people have decided to enforce to make sure that your phase field becomes only grows, basically, that the rate is larger than 0. The most commonly used is the one developed by Mie in 2010. It breaks the variational consistency, so some of the people are critical of this and they have other approaches, but I must say it's quite widely used. And the idea is simply to replace, in the phase field equation here, replace this strain energy density with this H, which is called a history field, and is defined basically as the maximum in time of this strain energy density. So basically, you're just making sure that this term, that your driving force for fracture doesn't go down. If it goes down because your strain energy density is going down, your phase field remains the same. It doesn't go down.
Sign on refers to the initial crack length, the pre-existing crack, or even before crack starts. Sign on.
So you apply it all the time. So it's what do you mean with respect to the initial crack length?
The side knot, the zero, sub-zero.
Oh, sorry. The sub-zero, what it means is the undamaged strain energy density. So yeah, sorry, good point. I'll clarify. Every time I use a 0 index here will mean that I'm talking about undamaged quantity. So stress without a 0 will be the damaged one, and sigma 0 will be the undamaged one.
So B is 0 everywhere at that point of undamaged situation.
Yes, undamaged 0 will be undamaged situation everywhere.
B is 0 everywhere.
Yeah, correct. It doesn't mean that the phase field is 0 everywhere. It means that, let me go back to the. So I don't think I have a good. I can make I'll put it in the blackboard. So we normally have something that is a degradation function. Maybe we don't need this anymore. In phase field, we have a degradation function that we normally define. Some other people have defined in various ways, but we normally define something like this. It's a quadratic form. So when the phase field becomes equal to 1, wherever you are degrading is fully degraded. That's the idea. So normally you have a stress tensor. I'm going to just, that will be something like this. And this will be the 0 stress tensor. So you'll be at a damaged stress and undamaged one. And the same goes for the strain energy density. So I'm not sure if I've always used the right notation in my slides because I'm mixing slides from various sources, but that's the idea. So you have an undamaged quantity and a damaged quantity after multiplying with this, before multiplying with this. And of course, what drives the driving force for fracture is the one that is undamaged. Otherwise, it will be degraded, and then you lose at some point your fracture driving force. It's your energy that is accumulating in your material. But yeah, this will be the notation. So whatever you see as 0, that means undamaged quantity. Then without the 0 means multiply by the degradation function. That's the idea.
This history field should be, every time should be maximum at different time interval, right?
Yes, so it basically stores the maximum of the strain energy density. So
each element or a whole system?
no, so everything, all these quantities are, this is a strong form, so everything is solved in the local, so every point you have a different history field that will be the maximum of the strain energy density in that history field. So it's maximum in time, not in space. Yes, exactly. So that's the idea. You basically, in every point you're solving that equation. In every point you're storing your strain energy density. That gives you a phase field in that point. But you need to make sure that your strain energy density, your fracture driving force doesn't go down, because then otherwise you will reheal your material. So your history field is there to prevent that. It's just storing the maximum of that strain energy density at that point. That's the point.
So stress, like let's say we consider a point at which crack has not initiated as well. And stress 0 is the point, is the last stress applied at which the damage is not happening. It's not the initial.
Okay, so let me clarify that aspect. So this is more or less what you see in continuum damage mechanics. So in continuum damage mechanics, what you think normally is that if you have, let's see how I draw this. So if this is the cross section of a bar that you're pulling, if you have some crack material, something like this, let's say all these regions are crack regions, and let's assume that this means that 50% of the domain is cracked, more or less. This will mean that either your phase field or your damage variable will be equal to 0.5. So then if you think of the force that this thing can carry, it's half of the area that you have there. So you have two quantities. You can determine a stress, from the force over the whole thing, which will be the undamaged one, or the damaged one. So it's kind of the same as in continuum damage mechanics. So if you are interested in the stress, this is basically an integration point where I'm looking at a microscope and I'm seeing something that is neither fully cracked or uncracked, something in between. So here you will have a stress that will be related to this. So some people talk about effective stress or damage stress. And there will be the entire thing, the homogenized version. That will be the fully damaged stress. Because what is the stress of this integration point? It will be the load that can carry, it can only carry in this area, right? 50% of it. And then you have also the stress, so this will be the stress of maybe of the whole thing. And then you have the stress of the undamaged region, which will be the sigma 0. So in continuum damage mechanics, often you say, okay, for example, if you look at the books of Simo and so on, they will say, if I care about something is yielding or not, normally they will use this guy, because they want to know if the uncracked material is yielding or not. But then when you talk about the behavior of the quantity itself is the damage stress. That's the idea. So you always, basically this is like a damage variable. Every time you multiply something, you can have, and this is the final quantity in a way. So at the end, your load current capacity of your material will be given by this homogenized stress. That is the damage and the undamaged. But on occasion, you may want to use the undamaged one also to understand things in uncracked regions, so to say. That's the idea. But initially, you could start with 0. Everything is the same, so phase field is equal to 0. These two guys are the same. And then some sort of damage is starting to develop. And then this becomes a bit lower because of the damage. That's the idea. So if you plot it ahead of a crack, your stress ahead of a crack are, I guess, in linear elastic fracture mechanics, infinite. So your stresses are going up. This is sigma yy, for example. This is distance ahead of the crack. And your damage one will be something like this, will be the same, but then it will go down because the phase field is going up in that area. And this is kind of the final stress that you get, the effective one. Okay, so that's the idea. You have, so often when you see the implementation, you will see a line of code that says, it stores the maximum value in time of the strain energy density, and then you see an H in the governing equations. That's something you'll find in many, many papers. The other thing I wanted to say is that so far I'm talking about the so-called AT2 or conventional phase field model. Is the first phase field model and is the one that most people use, the one developed by Bourdin and so on. But in reality, at the end of the day, if you go back to this, so this is the idea. Huh? This is Griffith. This is a variational approach to Griffith. But then we made a jump. We brought the phase field here, and we made some choices. As humans, we decided that, okay, we're going to degrade things like this with this quadratic form. It could be a 3 there. It could be a 4. It could be any other number. And then we also made a choice here. Okay, we need some sort of gradient to describe this smooth interface. But what comes in front of that gradient or what comes here, what coefficients, that some people, Bourdin and colleagues, decided to pick that thing. But you could have picked different ones. And whether you pick ones or the others will change basically the shape of this. So it could be that you say, okay, this shape, I mean, in my opinion, this does the job for most materials because the shape doesn't matter that much. We know that from cohesive elements. But you may argue, I have a particular material where I think the softening shape should be a bit different, or so it might be occasions where you want to use a different model. So people have developed other phase field models, and there are various out there. The most popular ones, I think it's fair to say, is, well, first the 82 model. And here, by the way, this is the expression. So far I've been talking about the expression related to the 82 model, but you can express the phase field equation as a function of other parameters that they'll make it more general. So you can define as a function of, this is G, the degradation function, so this is the derivative of G. This is the one I wrote there. This is what we call a geometric crack function. Here is the derivative there, and then this is a scaling constant that depends on the geometric crack function. So for the case of the 82 or conventional phase field model, these are the choices that people made, and as a result of this you get C equal to 1/2. There's another very popular model called the 81 phase field model. This 81 phase field model, I think the main difference with the 82 is that you have sort of a threshold below which damage does not start. So if you go back to that traction separation law, sort of traction separation law here, you will see that even before reaching the critical stress, some sort of damage is appearing because this is no longer linear, it's deviating a little bit from linear. So in fact, with the 82 model, because there's no threshold for the phase field, even from the beginning of your calculation when you're doing, so for example, when I'm plotting these kind of results, any of these results, this one for example, here everything looks blue, but the phase field is actually not completely zero. It's maybe 0.0001 or something along those lines. So the phase field is never really zero because, you know, the strain energy density is never zero. So that's the idea. So the phase field, the 82 model, maybe go back to this kind of traction separation law. I think this is the best way to discuss it. Yeah. So the phase field will never be zero. There will always be a non-zero value because, you know, the equation is such that this guy is never zero as long as you have mechanical load, of course. And because this guy is never zero, the phase field will never, you solve for the phase field here, it will never be, you see it here. You know, as long as the strain is non-zero, the phase field will not be non-zero. Of course, if your strains are very small, the phase field will be very, very small. So effectively, it's kind of zero, basically. It's not exactly zero, but it's kind of zero. However, you know, at some point it becomes a bit, you know, it starts growing and growing, and then eventually becomes big enough that you get this drop in the softening behavior. That's the idea. So the point is that some people argue that maybe it would be good to have a situation where you have basically a sharp threshold. So no damage starts until a certain condition is met. And that's what comes to this 81 model. So if you plot the 81 model, that kind of sort of traction separation law behavior, you get something that is completely non-zero and then, so completely linear, and then it goes down, basically. That's the idea. I mean, from an engineering point of view, I have never seen any problem where this actually made a big difference. Okay, it's not zero, but it's nearly zero. You actually, when you plot, I'm not playing with the legends. I'm just using the legend that comes out of whatever, any package I use, and you see it all blue because it's tiny. Well, some places it's close to 1 or 1. In these areas where whether it's 0 or 0.00001, it doesn't make a big difference. So I don't have a strong view on those things. But you must know that these models exist. There are multiple models out there.
CW, are they different?
Sorry, they're the same. That's a typo. I should have CW. Thanks for noting. Yeah.
So there is a lot of variation in the results of 81 and 82.
There's not a lot of difference now. There's not a lot of difference. You could think of, if you work with cohesive elements, you could think of a slightly different traction separation law, so to say. So it's just the threshold. So 82, you have damage already from the beginning. It's just tiny everywhere. Well, 81 has this very sharp threshold until damage doesn't occur. And so one way of implementing 82, there's multiple ways, but it's by defining some minimum history variable such that you don't grow here. This is 0 until you get this number. That's a way of thinking about it. And then the one that is a bit more maybe different is this phase field cohesive zone model that was developed by Wu and also some people in Monash. This phase field cohesive zone model, I think the motivation was to simulate more concrete-like materials. And then he used a completely different degradation function with, you know, you can pick different, depending on what you want to get, you pick different D values, A values, B values. The A value has this strength here, Ft. Ft will be the tensile strength. And the idea here basically was to, I'm not going to get too much into details, but the idea was twofold. First, you know, to have a more flexible approach where you can play with that kind of softening law. So if you know more or less the softening law of your material, you can use different softening laws. But also to kind of separate a little bit. It's not completely separated, and the length scale results are also length scale dependent. But to try to come up with something that is more or less length scale, a bit more length scale independent, and where you disconnect the strength and the length scale. And this has also been recently done by the group of Tom Hughes and UT Austin. But in general, this is the idea that you want to have separate the length scale from the phase field length scale. So in these other parameters, there's a relationship between the length scale and the strength. Here, you cannot separate them. You have an extra variable, the strength, but at the same time, you define your phase field model in such a way that you are less dependent to the length scale. So your result, you change the length scale a little bit, you won't see any difference, but then you have the strength. And this, I mean, it's kind of a philosophical discussion, I would argue, because first of all, we know that the strength must matter when it comes to designing the size of the fracture process on. So it makes sense that somehow by picking a nail, you change your strength of your material, because depending on the size of your fracture process on, you have a different strength in your material. That being said, there's no reason why the relationship that we find for the 82 model is the best relationship, or the relationship that works for all materials. So maybe having the flexibility of defining differently the length scale and the strength is an advantage. I mean, these are particularly popular in quasi-brittle materials like cohesive cell models. I would say the phase field cohesive cell model, and yeah, I just thought I should tell you, because I think all of the three are very powerful, but depending on the papers and the applications, you may see people moving around these options. But at the end, it's just options that you pick when you pick your constitutive choices.
Emilio, maybe a thought on what the mathematical form needs to be for if one needs to develop a new proposal for G. What mathematical form does it need to abide to be useful in terms of stability or convergence?
Yes. So every time you need to define one of these things, you need to be careful, because you need to fulfill. So the derivative has to be equal to 0, when phi is equal to 0, and so on. So there's a few items that one has to take into consideration. So you cannot just come with any random value of G. You need to fulfill certain conditions. If this is, I didn't include those here. I didn't think people were going to define their own phase field models, but maybe I can say a few words about that as well. Yeah, thank you. Okay, the other aspect is defining the crack. So, by the way, you can see here, this is the analysis that I showed you yesterday. I simplified by only showing one curve, but you can see here multiple curves for 81 and 82 model. And you can see, for example, that the 81 model seems to agree a bit better with this condition that G equals GC when the mesh is fine enough. It seems that the 82 model actually overshoots a little bit your GC. Not too much, I should say. But one could, based on these calculations, one could argue that 81 maybe is a bit more, better aligned, more quantitatively aligned with fracture mechanics. I think it's not a big deal, this overshooting, because this it's probably within the scatter of the determination of your fracture toughness when you do an experiment anyway. But it's there. It's important to know. The other thing is that you will see that in a lot of papers, when people define the initial crack, they follow two approaches. Either you can define your initial crack as a geometry. So you could define this. Imagine you have a plate with a crack. So I guess there's two options you can do. You can define your crack. You can define it in your finite element. You just draw the geometry of the crack. If it's infinitely sharp, often you have ways of basically duplicating nodes. You pick a line and you say, I'm going to duplicate my nodes, so that the moment you pull, those nodes separate from each other. But there's some people that would also argue that it's better to define the crack, making the phase field as initial condition equal to 1. So just picking these nodes, and saying here, my phase field is going to be equal to 1. And you could do that. I mean, it's a variable that you're solving for. So you could say phase field is equal to 1. You can enforce it in the nodes. In the same way that you enforce an initial value for the displacements, you could say the phase field is equal to 1. And there's a bit of discussion on, again, putting an engineering hat on me, I don't see a big difference. So it's completely up to you. But it does seem, as you can see here, that to be slightly better maybe, in the sense that it is a bit closer to this equal to 1 thing. And people have shown that this is due to, I mean, we have argued this, I guess. So if you plot, every differential equation comes with some boundary conditions. In this case, the Neumann boundary condition for this equation is this one here. So it's the gradient of the phase field has to be equal to 0 in the boundary. So if you don't prescribe in phi equal to 1 in a boundary, that will be a Dirichlet boundary condition. If you have a Neumann boundary condition, basically you are forcing your gradient of phase field to be 0. So imagine if you have if I plot here ahead of my crack instead of the stress, the phase field, and I'm looking, maybe I'm looking at this crack. Maybe I'm plotting the phase field around here. So this is no distance to the crack, it's somehow vertical distance. So the phase field is going from 0 to 1. If you prescribe the phase field equal to 1, then you may have something like this. If you don't do anything, you have this Neumann boundary condition at the surface. Maybe it looks something like this, but here, because you need to approach with a gradient of 0, maybe it becomes something like this. I mean, I'm simplifying things, but it's just for you to understand that because you are forcing the gradient to be equal to 0, you may end up with something like this. So it's maybe slightly different. So what people argue is that there is an energy cost when you don't define anything, when you define your crack geometrically, because you are enforcing that Neumann boundary condition, there's an energy cost associated with it. And therefore you need to apply a bit more energy to grow the phase field, right? Because the phase field cannot just start appearing. You need to jump in a way. You need to have enough phase field there. That is the idea. So again, not a big effect, but there is a bit of an effect. So some people prefer to apply this phase field equal to 1 to define where cracks are. And often it can be very convenient because you may have a very complicated crack geometry, multiple cracks, multiple defects. I'll show an example in the seminar. And then you can just define the phase field equal to 1, and you don't have to define a very complicated mesh or geometry. You just pick a region and say, I have this funny. You do not only need to model cracks, you can model any sort of defect. So you have a defect this size, and instead of making a complicated mesh to reproduce this bottle, you just pick all the nodes inside of the geometry of the bottle, make it equal to 1 to start with, and then continue. Yeah.
Having the only Neumann boundary condition will lead to multiple solutions, since we are not specifying the dictate boundary condition p equal to 1.
No, it will not lead to multiple solutions. Why do you think it will lead to multiple solutions? Because you have...
Like we can specify 2 dictate boundary conditions, or 1 dictate, 1 Neumann.
Yeah.
But if we specify only Neumann boundary condition, will lead to multiple solutions.
But you have an initial condition for the phase field. So the phase field condition is equal to 0, and you have the Recurrent boundary conditions and Neumann boundary conditions for the displacement field as well.
Oh, we specify dictate also.
You have initial conditions, for the phase field.
Initial condition and Neumann boundary condition.
You could. It depends on what you want to do. So it's like every other problem. You can apply displacement boundary conditions, the Dirichlet or Neumann. You can apply attraction, or here you can apply this kind of phase field traction, so to say, or you can leave it as phase field equal to 0 and apply an initial condition.
Continuing this question, if we have a two-dimensional pitch crack plate that you have drawn like that, what would be the initial condition on the field?
So if you define it as a geometry, you think? Yeah, phi will be equal to 0 everywhere. That will be always the initial condition.
Every point.
Yeah.
Except the crack faces.
So if you decide to define your crack geometrically, you just define phi equal. So whatever, you don't need to do anything then. The initial condition will be always phi equal to 0. So you don't do anything. You just put a crack geometrically and you start loading. If you want to define the phase field equal to 1, then you define phase field equal to 0 everywhere else and phase field equal to 1 in the nodes of the crack.
In progress, as it progresses, it becomes 1.
Yes. Automatically, it will this equation will evolve, and the phase field will start growing everywhere. I wanted to say these things, but one should not think that the modeling is actually quite straightforward. So you could just define your sample with a crack and start pulling, and things happen. And there's nothing else you need to think about. But if you start looking at the literature in phase field, you will see sometimes people doing these things, and I wanted to just give you a heads up, just so that you know what is behind it, the motivation behind it. The other thing is that Griffith does not, so it's what we call the strain energy decomposition. So if you think of a 4-point bending, for example, or a 3-point bending. So in 3-point bending, you have something that might look like this. Maybe you have a notch here. And then maybe you're increasing this guy and keeping those constant, right? This is the classic 3-point bending. So you may accumulate some phase. If I run the simulation with phase field, you will see that the fracture will be driven by the strain energy density, the driving force for fracture. This is what we discussed. So the phase field will start growing here, but it might also grow here and maybe here and here, because if you think of a strain energy density, your stresses and strains are also quite high there, particularly depending on how you distribute your load. If it's a point load and so on. So this, of course, it's again a bit of a philosophical argument. If you do a test with a concrete being in a lab, you will see damage appearing here, but also there and there. So in a way, maybe it's sensible. But some people will argue that the damage should only appear under tension. And some materials is very clear, we only see damage under tension. So then, it's not that Griffith is wrong, but in a way, our model will predict something that is unphysical, because we will be saying, if damage accumulates in areas where the strain density is large, we will have a strain density large in multiple locations where we don't want to see damage evolving. We only want to see damage evolving here. So what people have come up with is what they call strain energy decompositions, or splits. So the idea is that you decompose your fracture driving force, which is the strain density, into a tensile part and a negative part. There's various ways. One is the spectral split that was proposed by Christian Mie based on principal strains. The other one is the volumetric deviatory split proposed by Amor and co-workers. You can see the definition here. And then there's also the no tension split, which was proposed by Freddy and Roger Carfani for masonry-like materials. You can see it here. So the idea is that, you can use the one of Griffith. Normally that does the job all the time. But in occasion, if you're modeling something where in a compressive stress state, you can have a very large strain energy density, you may see some damage appearing there. And if you want to prevent that damage from appearing, you can use this sort of splits. So this is, there's various options. It's just whenever you calculate your strain energy density, instead of calculating it using the usual equation, you can define it something like this. You can have a positive term and a negative term. And then basically what you do is in the phase field, you use only the positive one. Sometimes you see H plus because it's the history field. But you use only the positive one. So only the positive one drives the fracture. That's the idea. So you have basically, you're kind of separating in various ways the tensile stresses and the compressive ones, and you're saying only the tensile ones are actually driving the fracture. That's the idea. So then if you apply that to this, then you will see that eventually this damage here disappears, this damage here disappears, and only damage appears there. Okay, so that's one part of the story. So when you define,
Does that mean that phase field doesn't count for the crushing type of cracks?
This is a very good point. It comes in 2 slides, but it's a very good point. So I'll let you know in 2 slides. But I guess, let me explain in two slides because it will be more clear more visibly clear. But then, okay, so you need to define this tensile stress or tensile component and compressive component if you wish. And then if you do that, then of course you need to make a decision. Okay, first, for sure you're going to use it in the phase field, otherwise you don't make any use of it. So that's going to drive the phase field. But then if you want to be variationally consistent, then you should also, make it like this in the balance equation, in the balance of linear momentum, in the displacement problem, basically. So then instead of degrading the full stress, you will degrade the tensile part and not the compressive part. So your stress will be defined something like this. But then in 2015, the group of Laura de Lorenzis proposed an approach that they call hybrid, where they say we change it here, but we don't change it in the stress form. And this is good because this problem remains linear, so convergence is a bit more easy, and they showed, I would say heuristically, that the results are more or less the same. The only thing you need to do is to change the driving force here, but then there's no need to change here. So you break the variational consistency, but you get something that converges much more easily, and that that gives you the effect that you want, basically, which is to prevent cracks under compression. That's the idea. So you will see a lot of papers as well where they talk about hybrid or they do this decomposition. Okay, so now I'm going to just answer that question. That was a very good one. So if you plot the stress field, the principal stress field you see here, sigma 1, sigma 2. So what Griffith is proposing is that you get a failure locus that looks like this. This is this kind of orange-like or yellow-like curve here. So you do get cracks under compression, but in agreement with this failure locus. And of course, not all materials follow that failure locus. So people would say, okay, when we talk about strain energy decomposition, it's good to prevent compression, but I guess when people started talking about it at the beginning, they were thinking of materials that fail under tension only. But as we just heard, we have materials that fail also under compression. I mean, in reality, if you look at it, what happens is things are failing under tension, right? You have micro cracks that are growing under tension, but macroscopically, it looks like things are failing under compression. For example, you have here graphite, and you see this is the failure locus for graphite. So you can see one of the principal stresses being very compressive here, this one too here. So it's quite a funny failure locus, I would say. So what happens if you want to develop those things? What happens if you want to develop, I don't know, for example, we work quite a lot now on kind of rock fracture mining applications where you're hitting a rock in various ways. So you not only care about tensile cracks, but you want to capture cracks in every stress state. So phase field, as you can see, if this is the phase field criteria, the one by Griffith, it's a symmetric kind of failure criteria, so it will do something like this. So it doesn't really capture these parts here. If you use splits, as you can see, you get different ones. So this is the no tension one. The no tension is really for brittle materials. Then you have the volumetric deviatoric, and this is the spectral. So you change a little bit. You have some options with those splits. And this is fine. I mean, there's a bit of discussion about the ability of phase field to capture nucleation cracks. This is what you see here, by the way. This is a classic paper by Tané and JMPNs a few years ago. So if you're dealing with nucleation of cracks under tension, phase field can capture this nicely. So you not only need to think of samples that are cracked, you can think of a sample where you have a notch or nothing, basically, or a hole maybe here, and you will nucleate cracks here naturally with phase field. You don't need to define cracks to start with. And phase field does a very good job in capturing the nucleation of cracks. You can see it there. But there is comparison with experiments on many, many materials, as you can see here. This is some sort of notch radius, different notch radius, and some sort of generalized stress intensity factor, so different toughness versus notch radius. You can see that there's a very, very good job in capturing the literature, so you can predict nucleation of cracks under tension. But what happens if we're interested in those compressive cracks, right, that we discussed before? What happens if you're interested in capturing the nucleation of a crack in graphite? So I know that in graphite, from my experiments, if I have this situation where I have this compressive stress and this sigma 2 positive stress, I'm going to nucleate a crack in graphite. And this is happening because of what's happening at the micro scale. Cracks are tensile driven, but at the macro scale, I can see that it's slightly different. So if you want to capture those things, then you need to come up with, again, different splits. Here you see some of the splits, but you see the splits don't fit graphite very well. So people are trying to come up with a way to extend phase field in such a way that you can basically input there any arbitrary failure surface that you wish. And there's various models out there. The most popular one, as I will argue, is the star convex model by the group of Laura De Laurentiis, Corrado Marini. We propose the generalized energy decomposition as well, which, for example, can deliver very nicely more Coulomb type of, or Drucker-Prager type of failure surfaces. There's also the group of John Dolbo, Oscar Lopez Pamíez, looking at non-energetic models. And then there's a group in France, Molnar, Triangle, with using this length-free phase field formulation where they again have a driving force where you can capture this. Yeah.
So is failure surface input in the phase field model?
Yeah, so by default, the failure surface that phase field will give you is this. So it's maybe fine if you're worried about tensile materials that fail somewhere here. If you add these splits, you can add them there. But if you want to do an arbitrary failure surface, because you worry about things failing in their compression, you want to capture the entire failure locus. You're not looking at applications only where, so basically you want to capture not only this, but you also want to capture this and this and this, as it happens in the experiment. Then you need to use some of these approaches, which is basically extensions of phase field. So sometimes they have an extra term somewhere here, or a strain energy decomposition that is much more complicated. There's various possibilities. They have a term that depends on your hydrostatic stress field as well. So there's various approaches. So you need to extend a little bit phase field.
But what if I don't know my failure surface? I start with the model and then try to validate
Ah.
it. Gradually what will.
It's an interesting question. I don't think any of these models will. I mean, depends if you're. I guess you can always approximate your failure surface to something like, more Coulomb type of failure surface, and then you just play with the parameters of the more Coulomb. In which case, these models will probably do a good job in that sense, in that you will. If it's something that looks nothing like any other model we have seen, like Drucker-Prager, more Coulomb, any failure surface like this, then it might be more complicated. But hopefully, most materials will stick to some sort of failure criteria like this, so you can just implement one of those and play with the parameters in principle. I mean, some of these models, or these approaches do provide general ways of coming up with your own failure surface expression. It's just it will be a bit more complicated. Yeah.
So here we are not using psi plus if we want to incorporate the crashing also. So now we are only using psi plus or some fraction of psi minus?
It depends on the approach. For example, if you use our approach to generalized energy composition, you are using psi plus. but it's a very different side plus than the one you saw before. It's a side plus that gives you a more Coulomb or Drucker-Prager type of strain energy composition. Because if you see here, this is, so the yellow one is no side plus, just a standard Griffith. The other ones is the side plus, and it gives you something, but it's not something that resembles Drucker-Prager or granite, or so it's basically changing your side plus. And there's other approaches. These other approaches use a slightly different thing, but it's more or less the same idea. Yeah. Okay, so that's the end of last lecture from today, and I think we can jump directly. Yeah, no, it's too early to do a break, so we'll jump directly to the implementation details, and when I see that you're a bit tired, we'll do a 5-minute break.